All right, recording's rolling. It is Monday, September 15th. So we're starting on a new topic, which is, well, I'll call it dynamics or forces. I did pull some puzzle questions out of your book over the weekend. I put these together. I did upload this to Google Classroom, so I have a stack of these binder clips right here. We're not anywhere near getting close to these today, so I'll have these up here. Okay, if you really want one of these, right, I'll look at these to you eventually. Then I do have them up here. You can let me know or got one. So I grabbed those up there, but I'll get those to you guys eventually. But today I want to do an overview of what this section is going to be about. It'll probably take us about 3 weeks. About 3 weeks to go through these. Have lots of labs lined up. Have of course house book puzzles. Right. So we're moving to where are we in the scheme of things? You guys remember very first day of school? I gave you guys these thumbnails. Okay. So all the silver banners, just like what we got here, basic math stuff, some algebra, trigonometry, right? Then some basic science stuff, scientific method, kind of stuff. Right. The red banners, that's what we just finished last few weeks. We've been working on. Got some linear motion, got some projectiles. Okay. We're moving on to these orange banners. Orange banners. Ooh, I got a couple pages of orange banners. Look at all these right here. All these oranges. So a lot of class today is going to be, I'll be going through a PowerPoint slide, a presentation covering a bunch of these slides. I'm only going to finish the whole thing today, but I'll get as far as I can. I'll give you an overview of what we're looking at. All right, so here's some of the main topics. We got Newton's laws of motion. We're going to be talking about forces. Now, all the forces just a push or pull. If I push on something, if I pull on something, right, here, if I hook this with a force and or with a spring scale, actually, I'm here. Let's start pulling. There's some kind of force involved in that. Um, Free body diagrams. This is a big deal in physics. It's just a diagram where you label what are all the individual forces that are acting on an object, and then you can make some kind of sense of that from there. Okay. Hey, do you guys think you're sitting on the second floor of a building right now? Second floor of a building? Do you think the engineers designing this building better make sure that whatever materials they're using, moving, whatever is like sitting on top of the floor, the floor is not going to crumble beneath us? Right? There's really heavy lab tables back there. Right? We're all sitting on the floor. Right? It's not going to crumble. At some point in their engineering analysis that they were doing three body diagrams at every point in the floor, make sure it's not going to crumble apart. We'll be looking at springs and what's called Hooke's law. So here I have a couple of spring scales here. I think you guys may have got your hands on these at some point. So here I got a brown scale and a red scale, and I've got some other ones back in the closet. But this brown scale goes up to 10 newtons of force. So if I stretch this, it takes 10 newtons to stretch it. The full distance goes up to 10 newtons right there. So I'm pulling with 10 newtons of force. Ooh, okay. This red one goes up to 20 newtons. Woo! Okay. Notice it's about the same distance to go. This one goes up to 10 newtons. This goes up to 20 newtons. So I pull it with the same force. It only goes up to 10 newtons right there. Pull double the force. Down to 20 newtons. You see double the force, it stretches twice as much. This thing is linearly scaled. It goes 0, 4, 8, 12, 16, 20. This one goes 0, 2, 4, 6, 8, 10 newtons. Like I said, linearly scaled. Oh, yeah.
How many pounds is one Newton of force?
Yeah, so one, how does it go? Well, here, I can say it this way. So that's a little tricky question because in the American system, pounds is ambiguous as to whether you're talking about pounds mass or pounds force. So sometimes they write this way. You guys know LB is the short for pound, right? I think it's like some Latin term, something, right? If you call it the pounds mass, you're referring to mass. If you talk pounds force, it refers to the equivalent force. Now, as long as you're locked into the surface of Earth and you step on a scale and you're talking about like equivalent weight or something, uh, okay, there's like some math that produces some weight at the surface of Earth, right? But the metric system is really good at distinguishing between what's mass and what's weight. Remember, earlier this year I was doing this. I was getting a sense of like how much inertia. And I said if I did this on the moon, would this feel exactly the same on the moon? Yes, it would, because this object has so much inertia, this is to say so much mass. And that doesn't change. But if I put this on a scale, or like a digital scale, or if I lift this against gravity, now that would feel entirely different on the moon. Because right now I'm getting a sense of how much weight, like how much force I'm pulling against, something like that. Right? Right. Again, the English system, the American system, not very good at distinguishing these two. Right? But the metric system does. So I can tell you guys this: 1 kilogram is approximately, I know this much, is approximately 2.2 pounds mass. Right? And 1 kilogram at the surface of Earth weighs 9.8 newtons. So it's like 9.8 newtons of force. And oftentimes I will round that to 10. Okay. So That's your largest lab weight. Right? So this is 1 kilogram. Right? If I do this, I'm feeling 1 kilogram of inertia. If I pick it up, it takes about 10 newtons to lift it. Okay. Or 2.2 pounds. Okay. So this is about 2.2 pounds. Right. All right. So you guys could. Yeah, so that's a good question because I never actually filled in that detail up to this point, but yeah, that's another reason that the metric system is really nice. Okay. All right, so when we look at these springs, you guys are gonna see this graphed out. Right? What does it mean that like double the force is gonna stretch this twice as much, and what does it mean that this one's not very stiff and the red one's really stiff? Okay. We'll be looking a little bit at inclines. So what if you actually you guys have worked with inclines already? Okay, you guys remember taking those Hot Wheels cars, up an incline, saying slides down. And so what does that motion look like? How can you make sense of that with diagrams? I don't have a pulley in front of me, but you can set up some outlets are pretty fun. We won't even get to these today, but if you set up a little pulley, you set up a couple of weights tied together by a string over the pulley. Right, zoom, zoom, zoom. How does this thing move? Right, those are fun. That'll be a whole lab, maybe 2 labs out of that. Friction. So if I push something across the surface, do I feel a resistive force from the fact that it's on a surface? Okay. What if it was on paper? Now it's even harder to push. On the slick wood, it's really easy. On the paper, it's really hard. What if this was sandpaper? What if it was wax paper? That would be close to like this, right? So it's like, yeah, here. So maybe some kind of material properties going on. Okay. Here, I'll show you this real fast. So my AP students, I did take a few minutes out of class to color their page. I think I gave you guys one of these AP type formula pages. If you were taking AP, they would give you this during the exam. Okay. So just in the big scheme of things, all we've really covered so far, like last few weeks of these 3 kinematic formulas, those are of course these here. They write them a little bit different on AP, but basically these we've been working with for a while. Okay. We're about to go into, well, pretty much just these orange ones right here is all I'm going to focus on for a few weeks. Okay. So we got this is called Newton's second law of motion. You'll see that on the PowerPoint. There'll be Newton's second law of motion. Acceleration is net force on total mass. Okay. There's a friction equation and there's a Slaw equation. Okay. And I circled some other ones that we're going to come up, probably about 4 or 5 weeks from now. Okay. So a little bit of context there. Okay, so we're doing posters. I do have a bunch of really good Paul Hewitt demos. I'll probably play at least a couple for you guys today, and if we have a little extra time, maybe some other ones. Do you guys know on Google Classroom? If you scroll back to the very first week on Google Classroom, you guys know I uploaded all the Paul Hewitt videos in a zip drive. Okay, so you could watch them for the entire year if you wanted to. They're all like a minute long. They're really good demos. Okay. All right, so any questions so far about what we're doing, where we're going? All right, so I pull up this PowerPoint and let's see. Again, trying to give you guys an overview today as far as I can. All right, so what variables and units are you going to be seeing for the next few weeks? So right from the top, M. Now you got to be careful with that because M could mean lots of things in lots of different contexts. As a prefix that stands for milli, as a unit that stands for meters. But here it's not a prefix and it's not a unit, it's a variable. Guys, as a variable, M stands for what? Mass. Aha. Okay. And we're going to measure that in what? Kilograms, quantifying kilograms. And maybe some of your labs that they might be in grams or something, right? But here, I'll tell you guys why a kilogram is important as the base unit, and not just grams, but you need kilo, which is a factor of 1,000. So you get 1,000 grams. Okay? Is look at right beneath it. You guys see F force can be measured in newtons, quantified in newtons. Yeah, the English system kind of goes with pounds, but it's kind of ambiguous. Like what's mass, what's force. The metric system is really good at distinguishing, right? Kilograms for mass and newtons for force. Right? Now, I'm going to come back to the slide, but this next slide right here. What is 1 Newton of force? What does that sort of like break down into? So 1 Newton of force breaks down to exactly 1 kilogram meter per second squared. So suppose you're out in deep space and you have that large lab weight, that 1 kilogram lab mass, right? It's just floating around. And you push on it with 1 Newton. So I'm putting 1 Newton of force on 1 kilogram of mass. Guess what that causes it to do? Yeah, it moves. It moves how? Guys, what is meters per second squared? What does that quantify? Acceleration. Aha! So put it all together. If you put 1 Newton of force on 1 kilogram mass, that's going to cause it to accelerate at, guess how much? 1 meter per second squared, because 1 times 1 is 1, right? What you guys just told me is Newton's second law of motion. That is Newton's second law. Right? You can see right here. It's sort of spelled out if you know how to read the music of those units, right? All right, so we'll come back to this slide. Go back here. All right, you guys good so far? And notice that this is kilogram here, right? So 1 kilogram meter per second squared. It doesn't say grams, it says kilograms. Right? So kilogram is the base unit. If you see m times g in this class, well, okay, careful. If let's say many years in the future, you're reading off a bottle, some medication that might be milligrams as a unit, but like, almost all the time in this class, it refers to weight. What it is, it's two variables multiplied. It's mass times gravity field. Can you guys get that? Mass times gravity field. Okay. You have some mass and some gravity field that conspires to make weight, sort of. I've always seen it that way, so I just stick to that. That was also Newton. All these forces are newtons, right? Something called a normal force. Hey guys, in math class, think back to math class. If two lines are normal to each other, that means they're what? Starts with a P. Perpendicular. Aha. So a synonym for perpendicular is called normal, right? So if there's some kind of support force from a surface, it's called the normal force. This gets a little tricky and a little fun if the surface is inclined. Ooh, what if you have like a 15-degree incline, right? That normal force is always normal to the surface, it's always perpendicular. You'll see some examples that way. Friction force. So friction is always trying to resist motion, slow things down. If you have like a table surface and some object sliding across it, friction is always going to oppose the direction of that motion, try to slow it down. Okay? And these are all in newtons. They're all different kind of forces. All right, now, speaking of friction, I have some slides later on. I'm talking about this concept called coefficient of friction. This is a material property. Like, what if you were sliding a lab weight across a wooden surface versus that lab table versus your desk, which looks really slick? What about wax paper, which is really, really slick, right? Hey, what if you're driving your car? Right, what if you're driving on dry asphalt or wet asphalt or an icy road? Guys, what's easiest to brake to a stop? Is it easiest to brake it to stop when it's a dry road or when it's a wet road?
Dry.
Dry, yeah, right. Anybody been way up north when the road is iced over? Yeah, yeah. It actually is probably better to not drive when the road is iced over. So some states they actually tell you to put like chains on your tires. I don't think we have that in Florida so much. What's that?
Winter tires exist.
Yeah.
Better.
Okay. Oh, and there's like winter tires and stuff. Yeah. Right. So yeah, the idea is that I'm trying to get you guys thinking about like hinting at what these coefficients of friction can be. It's some kind of material property, maybe between the tire and the road, or the tire and the ice, or maybe like a lab weight and paper. Or something, right? There's some material property going on here that tell you some ratio, right? Newtons over newtons, hence unitless, right? If you see, how about a tension in a rope? Like that could be a kind of force you could quantify in newtons. So I'll designate that F sub t. Every once in a while, I call it capital T, but sometimes I like to reserve capital T for time period. But yeah, so F sub t or sometimes capital T. Okay, and then if we're back to springs, if you see lowercase k, yeah, lowercase k, that refers to spring constant. It tells you how stiff the spring is. It's a quantity. How stiff is the spring? I had a brown spring and a red spring over here. The brown spring was not very stiff. The red spring was like twice as stiff. Okay? So what that means is it would take twice the number of newtons of force to stretch it some equivalent amount, hence newtons per meter. Okay, so you guys see so far? We're done. Okay. One more variable. If I flip to the next slide, pressure. Pressure, and we're going to quantify that in Pascal. So what is pressure? It's like force per unit area. Now, you guys probably know the American unit for pressure already. Because if you're pumping up your bike tires, you're going to quantify that in what? PSI. Yeah, that's pounds per square inch, isn't it? PSI, pounds per square inch. This has some force per unit area, pounds per square inch. Okay? And the metric system would be Newton per square meter. It's the same concept, right? Okay. How about, here, let's talk about pressure a little bit. So this is fun. I have a 100-gram lab mass here, right, which weighs, to pick this up, takes 0.98 newtons of force. Now, I'm going to round that a little bit to 1 newton. Can I do that? 0.98, it's basically 1 newton. So it takes 1 newton to lift this, right? Can you guys imagine a big old foam board that's 1 meter by 1 meter, like 1 meter stick by 1 meter stick? Right. Actually, if you look at the floor, is that pretty close to 3-4 tiles by 3-4 tiles? Right. So a little bit bigger than that. Right? But suppose I have this 1 newton weight stacked on like a big old foam board that's 1 meter by 1 meter. Right? That would be 1 newton on 1 square meter. Would that be 1 Pascal worth of pressure per square meter? Right. So that's 1 Pascal. Right. This guy's sitting on 1 square meter. It's 1 Pascal. Okay. Are you sitting in an atmospheric pressure right now?
Yes.
Yeah. That's definitely not the vacuum of space. We're definitely not in the vacuum of space. If you were, your saliva would be boiling, your blood would be boiling, right? Just from being in a vacuum, right? So we're not that. Right? So how many pascals of pressure are acting on you right now? Take a guess. you know what 1 Pascal is? It's one of these guys on 1 square meter. Um, but what do you think?
What's the Pascal again?
200? More. Oh, what's a Pascal? Okay, a Pascal is here's 1 Newton of weight. If I put this on a foam board that was 1 meter by 1 meter, which is well, I don't have enough space up here. You guys get it, yeah. 1 meter by 1 meter. Okay, that would be 1 Newton on 1 square meter. That's 1 Pascal. Right?
1,000 Pascals.
100,000. Yeah, actually, it's like 101,300 if you're at sea level, which we basically are. Right? So 101,000 of these. Right here, I'll quantify that in. Let's do it the American way. Guys, what if you have a really heavy bowling ball and it's like 14.7 pounds? It's like, it's a heavy bowling ball. It's 14.7 pounds. Can you guys feel that? Really heavy bowling ball, right? Right. And you put that on 1 square inch, which is about this big right here. 1 square inch. Wouldn't that be 14.7 pounds per square inch? Yeah. You know what that feels like? Well, you're sitting in it right now because that's also 1 atmosphere. Yeah, that's 1 atmosphere. So there you go. Give you guys an idea. Right, so that's fun. That might come back later. Newton's laws of motion. Let's talk about these laws of motion. So, first law of motion is also called the law of inertia. This is the one that says an object at rest will remain at rest. An object in motion wants to maintain its velocity. And you guys know velocity has 2 aspects to it. It's speed, but also direction of motion. Okay. That'll always be true unless an external net force acts on that object. Right? So, if anything, I should recap on this idea. You guys know that in physics, being at rest versus constant velocity, if you're along for the ride, from your own experience, you cannot distinguish the difference. Right? If the car's going 60 miles an hour versus going 10 miles an hour, there's still equivalent inside the car, right? Okay. Constant velocity. Right? Okay. Now, what can you feel inside the car? You can feel speeding up, you can feel braking to a stop, and you can also feel what? Yeah, turning, like steering wheel turning. Yeah, right. And in any of those 3 cases, there would be a net force acting on the car, right? Right, like the tires pushing against the road one way or another, forwards, backwards, or to the side. Okay. Right, so if anything is ever speeding up, slowing down, or is on a curved path, changing direction, in that case, you know there must be some kind of external force. Okay. Right. Let's talk about net force, guys. That word net force. That means like the sum of all forces, as if there was a single force. And here, I'll draw this out. So suppose I got this object sitting right here, about the middle of the paper. Right. And I put 2 forces on it. So I'm going to push up and I'm going to push to the right at the same time. Now, wouldn't that be 2 different forces? I'm pushing up and I'm also pushing to the right. Okay. But do you think they kind of conspire? Oh, here, what if I push up a lot and push to the right just a little bit? Okay. Here, I'll represent it this way. Okay. Do they conspire to, as if it was a single force pushing collectively up and to the right? Right? Is that? Here, I'll draw a diagram. So here's how we're going to draw diagrams this class. We'll put a big old dot right in the middle of the paper, or sorry, right in the middle of the object. Okay. And then from that dot, I will extend the forces outward. Remember, so the force upward, there was a huge force that way. And the force to the right is just pushing a little bit. So maybe force right is just a little bit. Right? But those were 2 individual forces. But the net effect would be up and to the right, wouldn't it? Okay. So can I connect these tip to tail? Take this one and slide it up. Connect it tip to tail with this guy. And then from the tail of the first to the tip of the last, doesn't that create this big old resultant right here? Isn't this the resultant? Right? And this resultant is the net force. Right? So it's as if that's the only force acting on the object. Okay? Okay? You guys got that? And so it'll move that direction, or I should say it'll accelerate that direction. Ooh. Okay? Right. How about Newton's second law of motion? It says how things accelerate. Okay? So acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. You guys see this equation in the bottom left side? So how much something accelerates, you guys know what acceleration is. It's rate change of velocity. So in a linear sense, it could be like how fast we're speeding up or braking to a stop, something like that. Okay? So do you guys see if you triple the net force? Guys, if you triple the net force, what happens to acceleration? Does it also triple? Yeah. So like could 1 over 1 be equal to 1, but 3 over 1 is equal to 3? So you triple the force, you triple the acceleration. Everybody sees that, right? What about this? What if you leave the net force the same, but you triple the mass? So you have like a little tiny tennis ball. You triple that, and now you have like a heavier ball, maybe like a bowling ball or something, right? So for the same force, if you increase the mass, what's happening to the acceleration? It's getting what? smaller. Do you guys see that? Right? So for the last few weeks, you guys have actually been using acceleration. Right? You said, let's say if I drop a ball off a cliff top, it'll accelerate as it's falling down. Or my car in incline lab, right? I know the car was speeding up as it was going down the incline, right? Uh, but now we're getting to address like why that would happen at all, right? Why would anything speed up or slow down or eventually go around a curve, right? Working towards that, right? It's because there's a net force acting on a mass, right? More force, more acceleration. More mass, less acceleration, right? So I usually prefer to have the fraction form. Oftentimes, you'll see it in the non-fraction form, which is F equals ma. You guys have probably seen this in the past, maybe F equals ma, right? So that's what that is. Okay. All right. Is everybody okay so far? That's good. All right. Newton's third law. This is the equal and opposite rule. It says for every active force by object A on object B, there's a reactive force equal in magnitude, opposite direction by object B back on object A. So I've got a couple examples down here. Suppose there's a cannonball and a cannon, and there's some explosion inside the cannon barrel, and pow, right, out goes the cannonball. Right? Right, you guys see that? Imagine that. Now, is there a force on that cannonball while it's in the barrel? Yeah, definitely. Is there a force back on the cannon? A recoil force. Yeah, okay, but which force is bigger?
Amy?
Equal. They're the same. It's the same force, right? Guys, inside the cannon barrel, it's a trick question I ask every year, right? It's a inside the cannon barrel, there's just some explosion that happens, and from the point of view of the explosion, it isn't just like pushing equally in all directions. Yeah, it pushes equally on the cannonball forward as it does back on the cannon, right? Same thing. Right? Now, the effects are different though, because guys, according to after the explosion, because of the explosion. Which actually accelerates more, the cannonball or the cannon? The cannonball definitely accelerates more. It gets like more of an effect in terms of its motion, but that actually kicks back to Newton's second law of motion. So it's the same magnitude force on the cannonball and the cannon, but the cannon has way more mass, therefore it doesn't accelerate nearly as much. Yeah, so there's a recoil motion from the cannon, but it's just not as much, right? How about the moon orbiting the Earth? So eventually, several weeks from now, we'll get to maybe like orbital type motion. Okay. Is the Earth pulling on the moon gravitationally? Yeah, this was keeping it in orbit eventually. Okay. Is the moon pulling on the Earth?
No, but.
Yeah. All right. Okay. Isn't that what causes the tides? Right. Something about the tides, two tides every day because we have a moon. Right. All right. All right. But which force is bigger?
Equal.
Equal and opposite. Guys, it's the same force. The Earth pulls on the moon exactly as much as the moon pulls on the Earth. I can show you guys that here. So I stole this from a very old Veritasium video. You're saying, well, suppose you have a planet and a moon, and maybe the planet's like 3 times the mass of the moon. What if you thought about these like kilogram per kilogram? So what if you just isolate it to this kilogram versus this kilogram? You just look at this one and this one. Wouldn't those maybe even intuitively be pulling equal and opposite? Right. And then let's say you bring in a second kilogram up here. When this one have to be pulling equal and opposite, and then this one equal and opposite, right? So if you look at it kilogram by kilogram, and you see the accumulative effect, suppose it's like 10, 20, 30. If this is 30 newtons being pulled to the right, isn't this 30 newtons being pulled to the left? Yeah. Okay. Right. So even if they're different masses, the forces are always equal and opposite, right? Here, I'll do a little Paul Hewitt break here. So, on here. I play a couple of Paul Hewitts for you guys. He's got a lot of good ones, so just play at least a couple.
And what do we have down here, gang? We have some plates. No staples, no Velcro. The tablecloth. This is what I want you to do over the weekend when you get invited to dinner at someone else's house, okay? What you do is they say, hey, what are you learning at the university? Say, I'll tell you what I've been learning at the university, okay? And get the table all set. Grab the tablecloth like this and say, do you believe in the first law of inertia? And they say, yes, we do. Hey, how about that?
Ooh, so law of inertia. All those dishes want to sit right there because they got so much inertia, so much mass.
And you fire a rifle. Here's the bullet. Bullet races out. And the bullet has a force acting. But that gun kicks back. How much force? Really the same? The same. The same force acting back. Now, the acceleration of a bullet, a lot or a little? The answer begins with an L. A lot. Because here's the mass of the bullet. Here's the mass of the rifle. So here's the acceleration of the bullet. But here's the acceleration of the rifle. So the rifle only goes back to here. In the same time, the bullet goes from here to here. That bullet is accelerating like bonkers, right? Inside the barrel. Now, when it gets outside, is it still accelerating? No, it coasts. We talked about this before. It's accelerating down. Why it drops. So it follows the curved path. But while it's inside, the forces are the same, but the masses are different. That means that the effects are going to be different.
Ooh, the effects being the acceleration. Okay, so you guys go with Newton's laws. Newton's laws, that's good. All right, moving on. Okay, so here's a bridge poster. Ooh, acceleration could be a bridge variable between what we've been doing for the last few weeks, that kinematic type motion, and then this dynamics, why would it accelerate at all? It's something to do with the force, right? And so you guys remember those three kinematic formulas we've been using over and over and over. Right, so all I did on the left side here is I just rearranged them to solve for acceleration. So like the first one, second one, third one, you can rearrange it and solve for A. That makes sense, right? Okay. And then here's the new way to think about acceleration is Newton's second law of motion, right? Acceleration results from a net force acting on a mass, right? All right, so now you can connect these ideas together and you can create a broader picture. So if I threw a question at you guys like, some guy kicks a soccer ball with some force for some amount of time, maybe like a tiny fraction of a second, how fast does the soccer ball leave his foot, right? That could be a good question. And this is exactly how you solve it. This is the whole roadmap is right here. Say, okay, well, he kicked the soccer ball with some force that maybe I gave you so many newtons of force. Maybe I gave you the mass of the soccer ball, so you divide that out, right? And that tells you how much the soccer ball would be accelerating while he's kicking it, right? If I told you he was kicking it for like a tenth of a second, then you go over here, that t would be like a tenth of a second. And if the ball started from rest, that'd be not zero, and then you can calculate how fast the ball leaving his foot. You see, it's all right there. It's all right there. Pop, 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 right there, right? Okay, and a bunch of questions you could ask, in different ways. The bottom half of this poster is the rotational equivalent. Okay, so at some point this is going to pop up. So I pulled a turntable out. Okay. Got this turntable here. Now, we're not really turntable physics yet, but eventually, see, how could you relate, what's going on here? Like, do you think there's some friction force maybe holding this lab weight on here? Something like that. Where is he going with this? Okay. What if this turntable is speeding up spinning? Would that be some kind of acceleration, but maybe like in an angular sense, like speeding up spinning? If I let it stop, just go, it slows to a stop, right? But I'm not really thinking like a linear sense, like a car speeding up or slowing down, like moving forward or backwards. Right? It's more like like speeding up spinning or slowing down spinning. Okay, so that could be called angular acceleration. And like, how fast is this turning? Like, guys, does the Earth turn around one rotation every 24 hours? Right? So that's a certain type of velocity. It's called an angular velocity. Okay? And then, like, how far does this move? Could be like a displacement question, but maybe it's like an angular displacement, like so many degrees or so many radians, something like that. Right? And turns out that you can actually, I almost saw it before. You can actually take the three kinematic formulas that we've been using for the last few weeks and just put them in a turntable setting, which is actually what these three are over here. Right? But instead of how far have you moved in meters, it's more like how far have you turned in radians kind of thing, okay, and so on. Yeah. All right, so those are there too. Okay, so turntable physics, eventually going to pop up. Got that. Springs, Hooke's law. So I got some springs over here. So let's start with an unstretched spring. Not stretched, not compressed, just hanging out, right? And then we'll put a force on it to either compress it like the top picture or to stretch it like the bottom picture. See, like the bottom picture, it stretched some amount of X, right? And it took some force to do that. So if you say, what's the combination of, okay, like I put on some force and it stretches some amount. What if I double the force? Is it going to stretch twice as far? If it's an ideal spring, then yes, it will. And if you plot that on a force versus stretch amount graph, it should create a linear relationship. This is for an ideal spring to do something like that. Okay, is it? That's right. And the slope of this graph represents how stiff the spring is. That's what this K is. It's called the spring constant. Okay, so guys, imagine different springs. What if you had one spring that was just like a regular spring? You had another spring. It was like super stiff. Okay, well, let's do a super stiff spring. Okay, super stiff. Can you imagine? You have to pull really, really, really hard just to stretch it a little bit.
would that be like a point like way up here? I put a huge force just to stretch it a little bit. Can you guys imagine this would be a really steep slope, really steep slope, right? That'd be a very high K value, right? Maybe this one's like 100 newton per meter. Maybe this one's like 500 newton per meter. Right? What if you had a third spring and it was like a slink, like you put a little force in it, it stretches really easy. Could that be like a point like way down here? Right? Put a little tiny force and it stretches really easy, really flat type slope. Right? Well, not exactly flat, but pretty shallow slope. Right? Maybe that's like 10 newton per meter. Okay, you guys get that? Now next slide. Actually, before I flip, do you guys see this green triangle? We're not gonna talk about the green triangle for a few weeks, but this has to do with like how much energy it takes, like how much work it takes to stretch or compress it, right? Like I ate so many food calories this morning, therefore I have the strength to stretch it, right? So that's a future topic. Okay. Right. A lot of textbooks actually talk about Hooke's law in terms of the restoring force. Now, the restoring force is if you compress the spring, doesn't the spring actually push back the other way? And if you stretch the spring, doesn't the spring actually pull back the opposite way, right? Hence, everything would be negative. If I stretch it to the right, the spring's pulling to the left. If I push it to the left, the spring's pushing back to the right. Okay? So that makes everything negative. You just throw in a negative. Okay? But if I toggle back between these two, these are basically the same idea. It's just everything turns negative. If we're talking about restored force, we're talking about the applied force on this slide and the restoring force on this slide, but same looking equation. All right. I might have you guys one day do a lab version of this where I throw a bunch of different springs at you guys and figure out what's the stiffness of each spring, what's the spring constant, how many newton per meter. Some of these might be like 100, some of these might be like 500, some of these might be like 1,000 newton per meter. That's to say it would take 1,000 newtons to stretch it 1 meter if it could stretch that long. All right, free body diagrams. These are diagrams that we're going to label all the forces on the object, and in the future, some called moments. That's like torques, right? So we'll just stick to forces for now. Sometimes these are called force diagrams. I mean, there's technical differences, but normally I just call them free body diagrams. So we have some object, some scenario. I'm just going to label all the forces. Now, the rule, there's some rules with these. So we're going to identify the center mass of an object. We're going to label all the forces extending from the center of mass. Eventually, when we get to like rotation stuff, we might put forces at different locations on an object, but for now, we'll start just at the center. Okay? And notice these are all vectors, because forces are vectors. They're emerging sort of from the center, just as a diagram. Okay? And what about this note at the bottom? What is this? Velocity vectors are not part of free body diagrams. So if something's in motion, maybe you want to indicate it's in motion somehow. Guys, is velocity a force? No. Right. So velocity is just something to do with like how fast is something going, like a speed, right? But a force is like a push or a pull, right? Now, if you push or pull on something, that can change its velocity. But these are different concepts with different units, right? Force is measured in newtons, and velocity is in like meters per second, right? Something like that. Right. So what's some examples here? I'll run through these. Yeah, I have a whole PowerPoint just of free body diagram scenarios, and I took my favorite ones and put them in this one also. So you might see some of these by the end of the week, possibly. Okay. What if you have a spaceship in deep space and it's going constant velocity? Right. Guys, think about the scenario. If you're going constant velocity, what would it feel like inside that spaceship right there? Would you just feel nothing? Yeah, feel nothing. You're just floating around. Would you just be floating around? Isn't that true? Like International Space Station, you see the astronauts just kind of floating around, right? They're moving really fast. Right? They orbit the Earth every 90 minutes or so. I'm kind of ignoring the curved path part of that, right? But basically, it's just kind of floating around, right? So, same thing here. As long as the rocket boosters are not on, which would violate the constant velocity, that would make them speeding up. Yeah, they're just floating around. So there are no forces. See how there's a center mass dot, but I didn't actually draw any forces? Because there are no forces. You're just floating around. Right? It doesn't matter how fast the rocket ship is going. Right? Constant velocity. Because remember, in physics, if you're going constant velocity versus if you're at rest, inside the vehicle, it's indistinguishable. You cannot feel the difference. Right. How about air hockey puck at constant velocity going across an air hockey table? Right. Now, when you strike it with your paddle, like pow, that would be a force. Right? So I'd have to represent that. Right. But this is not that. This is after that's happened. So after you struck it with the paddle, it's just in motion. It's just coasting. Now, I did draw a fat arrow over here to indicate that it's in motion. So it's going across the table, right? But once it's in motion, you don't actually need a force to keep it going. Right? So there's two forces on this air hockey puck.
There's the weight pulling down, and there's the air just holding it up, and that's it. That's the only two forces, right? Now it's moving to the side, and the forces are vertical. Okay. Right. Actually, it's moving to the side just because of inertia. It's just going. It's just going. All right. I'll have you guys do this. Will be part of a bigger lab one day. Right? So what if you have a block and you pull the block at constant velocity across the table surface? You guys see, just like that setup, right? Guys, constant velocity. If the velocity is constant, what is the acceleration equal to? Zero. Zero. Isn't that true? Constant velocity is no acceleration, right? And as of today, you guys know if there's no acceleration, that also means there's no what acting on it? Force, no net force, right? Now, there might be individual forces, like that diagram right there. I'm looking at 4 different forces, right? But you guys see how all the forces sort of cancel out? Like the right and left forces cancel out and the up and down forces cancel out? So what are these forces? Right, so it looks like there's some applied force from the spring scale. So it's like you're pulling with the spring scale, pulling to the right. Right? But there is a resistive force called friction that's maybe trying to resist that. Right? This block has a, guys, what does mg stand for again in this class? Like weight. Right? So mass times gravity field, that could be like a weight. So some weight. Sometimes it's called F sub g. Sometimes you see that too. Right? And then, do you guys remember from earlier today what F sub n stands for? It's called the what force? Normal. Yeah, normal. And normal means what again? Perpendicular. You guys see how this support force from the table is perpendicular to that surface, which is just horizontal flat? You guys that too? Oh, okay, so it all goes hand in hand. What's that?
What happens when it's inclined though?
When it's inclined, here, I'll come back to this. What happens when it's inclined? I think there's an incline somewhere eventually. Okay, yeah, I didn't get this far in my earlier classes, but so, okay. But you guys see how the normal force is still perpendicular to the surface, but it's no longer straight up. Is that too? Right? In fact, it's a shorter magnitude than the full weight. So the full weight was like 10 newtons here. This might only be like 7 or 8 newtons. Okay. Yeah. All right, so let's go back here. So we're working towards that. Boom. All right. So I'll have you guys like drag a block across the surface, right? And you can read straight up the spring scale exactly what that force is. And therefore, if you guys suppose this force is like 3 newtons, what would this friction also be equal to? The same 3 newtons, just the opposite way, right? Because it's equilibrium, there's 0 net force, 0 acceleration to achieve constant velocity, right? It doesn't matter actually how fast you're pulling either. If you pull really fast versus really slow, now to get it in motion, there's some kind of net force going on, right? But once it's going, whether it's moving fast, moving slow, makes no difference. Get exactly the same diagram, right? And then would this normal force just be equal to this weight for this case if you just have a flat table? You guys see that too? Suppose the block weighs 10 newtons. Wouldn't this normal force also be 10 newtons? Can you guys see that? Okay. Now, what's with these boxes over on the left side, this green box and this pink box? So this is talking about the coefficient of friction. And again, there's 2 kinds. There's a kinetic kind and there's a static kind. Here, I'll start with the static kind. The static kind is, it takes some force to break the initial friction to get it going. So if I have this weight on this table, this weight, this table, like this, right? I'm trying to push. It takes a lot of force, and pushing more and more and more. Or if I was using the spring scale, maybe it's more obvious. Okay? So like right now it's at 0 newtons, 1 newton, 2 newtons. See, even up to 2 newtons, this thing still isn't breaking the friction from the paper, even at that point. Right? It's that, right? But if I move it up to like 4 newtons, okay, now it can slide across like that. Right? So as it's building up, those were all static cases, and the force was getting more and more and more. You guys see that inequality right there? Right, that's like to indicate that it's building up. Right, so you put a small force, medium force, you saw it breaking the friction at it. Now, once you break the friction, it actually switches over to this green box. That's like a kinetic friction case, right? And then it just becomes equals. Right? So once it's in motion, and that would be a material property. So I have a bunch of classic examples here, like wood and wood. So 0.5, could you interpret that as like half? All right. So basically what that means is for this scenario, whatever the weight is equal to, it takes half of that force to break the friction and get it to start sliding. If this block weighs 10 newtons, you can expect it to take 5 newtons to get it to start sliding. Okay? Now, once it is sliding, turns out you don't need as much force to keep it sliding. You only need maybe 30% or maybe 3 newtons in that case. Okay? Is that universal all the way down? It's all the way down for all these different examples. which coefficient is bigger, the static or the kinetic case? The static on every single one, and that'll pretty much universally be true. It always takes more force to get it going than it does to keep it sliding in motion once it's sliding, right? Because look at these last three examples here. Tires versus an icy road, tires versus wet asphalt, tires versus dry asphalt. Look at on the icy road, there's almost no friction at all. 5%, 10%. On the wet asphalt, medium. And on the dry asphalt, you get like the most, right? These kind of round numbers. It depends on exactly different kind of conditions, right? Is it new tires? Is it a new road? Oh, right. But how many guys got your driver's license? Who can drive driver's license? You guys have? Yeah. Now, did you guys, when you got your license, have to learn about something called anti-lock braking system? Did you guys learn that? ABS, anti-lock braking system? Yeah, yeah. All right, guys, that is also on the slide. It's this box versus this box, right? So let's take a little time travel trip. Right? So pull my time machine out of that closet there, and let's go back to the 1970s. Right now we're driving around the 1970s, right? So this is before ABS. Right? Suppose you have to brake in a hurry. You slam on the brake, and the car skids to a stop. So the tires locked in the 1970s, and the whole car skids to a stop, leads to big, ugly skid marks all over the road, right? And then people kind of figure out, wait a minute. That's taking advantage of, guess which kind of friction, kinetic or static? If the tires lock and the whole thing skids, that sounds like a kinetic case right here, right? Kinetic, right? So the old advice used to be this. Now, don't do this anymore, but back in the day, they used to say, don't actually slam the brakes. They would tell you to instead kind of pump the brakes, and the tires would roll ahead a little bit. And the idea was to gain traction with the road. So even though the tires weren't locked, they were actually rolling forwards a little bit. But wait, how does that make the car stop then? Because the cars were taking advantage of this other kind of friction. And they could actually gain traction with the road, and the car actually comes to a stop sooner. Okay, a little counterintuitive. Okay? Well, nowadays, guys, in the modern car, are you supposed to go ahead and slam the brakes fully?
Yeah.
Yes, because then the computer system takes over. That's what anti-lock braking is. And the computer will automatically roll the tires ahead a little bit for you to take advantage of this better kind of friction so the car stops sooner. Okay? Anti-lock braking. Right? All right, so Future Lab. Speaking of car braking to a stop. All right, here's a real classic setup. So let's run through this derivation. Now, at the end, this will tell you how much a car can slow down, like accelerate. Maybe this should be decelerate. I think I need to amend the slide. I'm going to change this in the future. I'm going to tag a negative right here just to really emphasize this is like slowing down for braking to a stop. Okay? What is this? So I'm going to start off, let's start off with the diagram. So here's the car rolling to the right. You guys see it clearly, it's rolling to the right. Okay? But there's three forces, and none of these forces are moving it forward. Okay? There's one force that is its weight pulling straight down. There's the normal force from the road holding it up. And then if this guy's braking to stop, isn't there friction between the tires and the road, effectively slowing down the car? Right? So the car is moving to the right, but the net force is actually to the left. Right? You guys see that too? Okay. So let's do Newton's second law of motion here. So Newton's second law, net force results in mass times acceleration. So that's okay, right? Okay. Now, in this case, guys, which force is the net force? How about this friction right here? Because don't the two verticals cancel out? The two verticals cancel out. So the friction force is the net force. So in place of net force, I can pop in friction right there. That's okay, right? Okay, now, the next line, I have to actually go back a few slides. You guys remember, like, these boxes right here? If I cross multiply normal force, wouldn't be coefficient friction times normal force is friction force? That be true? Okay, that might actually be a better way to write that. And that's exactly what's right there. You see that? But hey, as long as you're on a level road, isn't the normal force equivalent to the weight of the car? If the car weighs 2,000 pounds, I bet the road holds up at 2,000 pounds. That subs in right there. Right? And this tells you the rate that you're allowed to even slow down. Right? Because if there was no friction, wouldn't the car just never slow down? It would just slide forever. Right? So you need friction, and the better friction you have, the better traction, the more you can sort of like decelerate, I might say. Right? And it ends up being this expression right here. But guys, which variable canceled out? Which variable canceled? The what of the car?
Velocity.
True. Velocity ends up not mattering to the solution. What else ends up not mattering? The car's mass. The car's mass. You see, mass shows up as a variable in the derivation, but not in the solution. I don't see him down here. You guys see that? Right. Now, what does that mean? Right. How about this? Say you're driving in a car and you're you have a twin who's also driving an identical car. So two exact same cars. And one of you goes and picks up groceries at Publix. Here's my Thanksgiving groceries. So you got like it's like loaded up like the Grinch. Right? So you have a really heavy car versus a really light car. Right? And you're driving next to your twin car. Right? So everything is identical except one car is full of groceries and it's really heavy, and the other one's really light. You guys got that? You're driving side by side, like drag racing or something. Same speed, side by side. You both slam on the brakes at the same time. Which car skids further to a stop? What do you think? The heavy car, the light car?
The heavy.
Huh?
Neither.
Neither. How do you know neither?
Oh wait, cancel out.
Because the mass canceled out. That's what I've been leading up to the whole time. Look at that. Guys, the fact that the mass cancels out, that's a really classic question, by the way. Yeah, the heavy car and the light car take the same road to brake to a stop. Right. You guys see this right here? Playing at constant velocity? Here, guys, a couple minutes here. Here's constant velocity means you know the acceleration is what again? 0, which means the net force must be equal to 0. Okay, guys, this right here is a military entrance question. If you're thinking of going to the military, they're probably going to ask you this. Okay? So they'll say, what are the 4 forces acting on a plane? So you say thrust, drag, lift, and weight. And for this case, does the forwards and the backwards cancel out? Yeah, and does the up and the down cancel out? Yeah, and that would give you a case of constant velocity. Okay, something like that. All right, we'll do a little bit maybe with drag force. I know some books don't emphasize this so much, but the free fall we've been doing for a few weeks, there's just one force, it's weight. Now, if you bring in drag force, then you can eventually achieve a terminal velocity, but you have to consider air drag for that to happen. Right. So as this falls faster and faster, do you think the drag force builds up more and more? Right. And the equation actually goes like this. The drag force is proportional to the speed squared. So if you're going 3 times as fast, guys, 3 times as fast gives you how many times the drag force? 9 times because it's squared, right? Also, this cross-sectional area, isn't that why parachutes are really big? Right. So hopefully you can achieve terminal velocity fairly quickly and just very slowly come down, something like that. All right. Yep, that's about as far as I've been getting today. So yeah, that could be our pause point. I'll pick up about here tomorrow.